This is section 19 for our course. And we're going to start off with prep skills of adding or subtracting like terms. So when we're talking about an algebraic expression, we're going to put together bits of the expression that have the same variable with them. So for instance, on the first one where we have 10k plus 8 minus 3k plus 4, the ones that have the parts that have the k with them can go together, and then the parts that have the have no variable with them, just have a constant coefficient, can go together. And so the 10k minus the 3k becomes 7k, and then the 8 and the 4 becomes 12. And so you can do that with any polynomial type expression, which is where you have a number in front and then a variable, or just a constant like the 7 here. And so we're going to put, in this case, we can put the negative 7n squared with the negative 4n squared and make negative 11n squared. Then we can put the 11n with the 4n. They're both positive, so that gets us 15n. And then the plus 7 doesn't have anything to go with it. Let me differentiate these. So the 4n went with the 11n. Okay, so now our next skill, we only have 2 skills in this lesson, is to divide 2 terms by 1 term. So if we start off with something like 4n plus 12 over 2, we can split that into 2 pieces, both containing the 2. So you can do 4n over 2 plus 12 over 2. And sometimes that makes it easier to simplify, so like in this case we can cancel the 4 with the 2 and make it 2. So we have 2n, and then 12 divided by 2 is 6. And that's a lot nicer form than the 4n plus 12 over 2. Why can we do that? Well, we can do that because if you think about the way we add fractions, if we had, say, 3/7 plus 2/7, we would put those together because they have a common denominator as 5/7. Well, if we can do it that way, we can also do it the other way. So we could split 5 back apart into 5 plus 2 over 7, which then could be, oh wow, that was bad math. Hold on just a second. I meant 3 plus 2. And then we could change that to 3/7 plus 2/7. So this is the process that we've done. We've taken something that was split and then put it together, or put it with the common denominator in 2 parts. So we'll look at the prep skills questions. For A, we're going to put the 12x with the negative 4x, and we're going to get 8x. And then we're going to put the 7 with the negative 13, and we're going to get negative 6. So 8x minus 6 for that one. On this one, we're going to put the 4m squared and the negative 10m squared together. That's going to give us negative 6m squared, since that's a negative 10. Then we're going to put the negative 3 with the positive 7m, so negative 3m plus 7m would be 4m. And then the 5, there's nothing to go with it, so it's just going to be plus 5. So 6m squared plus 4m plus 5. And here, we don't have any like terms. There's a y cubed, there's no other y cubes. There's a y, no other y's. And there's a 9. So this is already in simplified form. I'm just going to put it in descending order with the highest power first down, but you really wouldn't have to do that, and there's no like terms to combine. So on this problem, we're going to split the 2 parts with the denominator of 4 in both of them. So 20x over 4 cancels and becomes 5x. And then 16 divided by 4 is 4. So that simplifies to 5x plus 4. On this one, we're going to get negative 12n over 6. And then we're going to subtract 96 over 6. Don't forget that that has a negative there, or a minus. 12 divided by 6 is 2, so we get negative 2n since it was a negative 12. And then 96 divided by 6, you can either simplify the fraction, or in this case, if it actually divides into a whole number, or divides out to be a whole number, you can put that. But even if it came out to be, say it came out to be 10 over 4, then you would still write 5 halves. You would still reduce that fraction, but in this case it turns to a whole number. So that's it for the prep skills, and we'll get into the regular lesson.
We're looking at this question. If you have 9 Supreme Court justices in a room and they all have to shake each other's hands, how many handshakes happen? So we're going to start small. In question 1, how many handshakes would there be if there were only 2 justices in the room? Well, then there would just be 1 handshake. And at the bottom they mention that we can draw that handshake as 2 dots and a line between them, which seems kind of pointless until you look at the next question. So question 2 is, let's add more people to the room. If there are 3 justices in the room, how many handshakes happen? Well, there'd be 1 between those 2 people, another between those 2 people, and another between those. So 3 handshakes. If there are 4 justices in the room, we'd have 1, 2, 3, 4, but then they also need to shake hands across the room, so 5, 6. If there were 5 justices in the room, 1, 2, 3, 4, 5, and then when you start drawing handshakes across to find the ones that have been missed, there would be 6 and 7, 8 and 9, and then 10. Now for 6 justices, around the outside, 1, 2, 3, 4, 5, 6, and then start across the middle, 7, 8, 9, 10, 11, 12, 13, 14, 15. And the picture starts getting messy, so we're going to need a better method than this if we're going to add any more people. So in number 3 it says take the answers that we already have from our diagram and fill those in. So 2 justices would only be 1 handshake, 3 was 3, 4 was 6, 5 was 10, and 6 was 15. And so the idea is to use what's called inductive reasoning to see if there's a pattern and then assume that it continues. So it looks like when we went from 2 to 3 justices, that added 2 handshakes. And then when we added another justice, it added 3 handshakes, and then 4, and then 5. So we can use that to form a hypothesis on what pattern we think might continue from there. Well, looking at that, if that pattern continued, we would add 6 now to get 21 handshakes, and then we'd add 7 to get 28 handshakes, and then we'd add 8 to get 36 handshakes for 9 justices. Here we're looking at the idea of a counterexample. So in number 4, every time it rains, my softball game gets canceled. So assume that's true. Our game was canceled last night. The conjecture then is that it must have rained last night in order for that game to have been canceled. But the thing you have to think about here is just because rain makes a game get canceled doesn't mean rain is the only thing that can make a game get canceled. So a counterexample would be anything that happened to make that game get canceled other than rain. So maybe the umpires didn't show up. In number 5, we'll look at a more mathematical example. So we've got an equation, and part A asks us to substitute -3 in for the x value. So we'll have y equals parentheses -3 plus 3, close the parentheses. Another set of parentheses, -3 minus 7, close those parentheses. Another set of parentheses, 2 times -3 minus 1, close those parentheses. So that gives us 0 times -10 times -7, and that comes out to 0. B says repeat that for x equals 7. Okay, so y equals, and we'll do that again with a 7 in for the x's. So we'll have 7 plus 3 times 7 minus 7 times 2 times 7 minus 1. And that's going to give us 10 times 0 times 13, which also comes out to 0. So if you were to use inductive reasoning here, you might think that that pattern was going to continue and that you could plug anything in and get y equals 0. So let's find a counterexample, because that actually is not true. Well, a counterexample would be any x value that you can plug in that doesn't give you 0. So perhaps x equals 0 itself. Let's try that. So y equals 0 plus 3 times 0 minus 7 times 2 times 0 minus 1. That gives us 3 times negative 7 times negative 1. And that does not come out to 0, that comes out to 21. And so that is a counterexample to the conjecture that y will always be 0. In number 6, a geometry example. These three right triangles, so they all have a right angle in them, are all isosceles, meaning that two of the sides are the same length. So the conjecture then is, perhaps every right triangle is an isosceles triangle. Well, a counterexample to that would be any right triangle that is not isosceles. So I could draw a right triangle with a short leg and a really long leg and then connect those. And in this one, none of those sides are the same length. So that would be a counterexample. In 7, we have an illustration here of triangular numbers, and we're asked to use inductive reasoning to find the next two triangular numbers. So looking at this, the first one has 1 dot, and then the second one has 3 dots because it's added a row of 2 dots. And then the third one has 6 dots because it took the triangle with 3 dots and then added another row of 3. The fourth one then took that triangle and added a row of 4. And so the question now is, what would the next two be? Well, it looks like we added 2 and then 3 and then 4. So to get the next one, we would add 5. So the fifth number would be 10 plus 5, which would give us 15. And then the sixth triangular number, we would take that answer and add 6, which would give us 21. In 8, it says these numbers should look familiar. These were the same as the handshakes for the 9 Supreme Court justices. And the question is, why would they be the same? Is it a coincidence? And it's not. If we look at this, so we talked about how each triangle adds a row with the next number in it. And if you think of the Supreme Court justices, every time you add another person in the room, they need to shake hands with everyone who was there before. So if we're starting with this first one being the handshake for 2 people, and then the next one is the handshake for 3 people and 4 people and 5 people, when you get to that fourth stage where you're adding a 5th person, that 5th person has 4 people to shake hands with. So that would add a 4, just like the triangular number. So here we have what's called Pascal's triangle, and so you're supposed to use inductive reasoning to figure out the missing numbers in the bottom 2 rows here. So looking at this pattern, we start with a 1, and then you can see that the 1s go down the outside on both the left and the right. The second row is just 1 and 1 then, but then when you get to the third row, the pattern changes, and there's another number other than 1. So it's a 1, 2, 1, and the idea is that the 1s above it got added together to become 2. And then in the next row, the 1 and the 2 adds together to give 3, and then the 2 and the 1 adds together to give 3. So that's why you've got 2 3s in that row. And so then in the next row, the 1 and the 3 add together to give you 4, the 3 and the 3 add together to give you 6, and then the 3 and the 1 add together to give you 4. So we can use that idea to continue this pattern. In the next row, we start with a 1, and then above it, the 1 and the 4 add together to make a 5. The 4 and the 6 add together to make a 10. The 6 and the 4 also give you a 10. and then the 4 and the 1 give you a 5. So that row would be 1, 5, 10, 10, 5, 1. And then in the bottom row, we need to start and end with 1s. And then in the middle, we look at the row above it. The 1 and the 5 give us a 6. The 5 and the 10 give us a 15. The 10 and the 10 give us a 20. The 10 and the 5 give us another 15, and then the 5 and the 1 give us another 6. So that row will be 1, 6, 15, 20, 15, 6, 1. So they have a number game for us to play. It says pick any number you like. So let's start with maybe a 3. And then it says multiply it by 8. So I'll do 3 times 8, and that's going to give me 24. And then it says add 40. So I'll take my 24 and I'll add 40. That's going to give me 64. And then it says divide it by 4. So I'll take 64 divided by 4, and that's going to give me 16. Then it says subtract 10 from that result. So 16 minus 10 gives me 6, and then subtract your original number. So I'll take that 6 and I'll subtract my 3, and that gives me 3, which is the number that I started with. Let's try it again with another number, maybe 5. So I'll start by multiplying that by 8, and that gives me 40, and then I'll add 40, which gives me 80, and then I'll divide by 4, and that gives me 20, and then I'll subtract 10, and that gives me 10, and then I'll subtract my original number 5, and that gives me 5. So it's starting to look like you will always end up with the number that you started with. That's what inductive reasoning would lead us to believe, and in the class portion of this lesson, we'll try and prove that for sure. So in the group portion of this lesson, we played a number game, and it looked like when we followed the steps that we were given, we would always end up with the number that we started with. Now, inductive reasoning just gives you a conjecture or sort of a hunch what might be true. We need deductive reasoning to prove it for sure. So number 1 says, instead of starting with a number, let's start with n, which stands for any number, and we'll multiply that by 8. Well, when you're working with a letter that stands for a number, or a variable, then multiplying that by 8 would give us 8n. And then in number 2, add 40 to that. So that's going to give us 8n plus 40. And then in 3, divide that answer by 4. So we'll take 8n plus 40 and we'll divide it by 4. And the easiest way to do that is to divide each term separately. So 8n over 4 gives me 2n plus 40 over 4 gives me 10. So now we have 2n plus 10. In 4, we're supposed to subtract 10 from that. So we had 2n plus 10, and now we're going to subtract 10. And so the 10 minus 10 gives us 0, so now we just have 2n. And then in 5, we're supposed to subtract our original number, which we were using n to stand for. So I'll have my 2n and I'll subtract n. Well, that's like 2n minus 1n, which gives me 1n. So that's the number that I started with. 6 wants us to think about how is this different from choosing examples like we did in the group portion of the lesson. Well, this time we didn't choose a specific number, we chose an arbitrary number that could have any value. So we've shown that no matter what the value we choose, it will always work. Here we're going to try to use a general approach with arbitrary values to find a formula for the number of handshakes for the Supreme Court justices that would let us find the number of handshakes for any number of people. So in 7, pretend you're one of the 9 justices. How many people's hands do you need to shake? Well, you need to shake 8 other people's hands. In 8, choose one other justice. How many hands does he or she need to shake? Well, that person is also shaking 8 different people's hands. And so in 9, if we think about this, if there are 9 people in the room, every single one of those 9 people is shaking 8 other people's hands. So how many handshakes is that total? Well, 9 people, each shaking 8 people's hands, so that's 9 times 8, which is 72 handshakes. Now in 10, that result doesn't match what we got earlier in the lesson when we used inductive reasoning. We thought that it would be 36. Explain why it actually is 36 and this 72 is twice as big as it should be. Well, if you think about that for a second, if I shake your hand and you shake my hand, that's not 2 different handshakes. That's really the same one. So we've double counted all of these handshakes. We actually need to divide it by 2. So then in 11, let's try to write a formula using that line of reasoning that will always work. So 9 was the number of people in the room. Let's call that N to be more general. And then each of those 9 people shake 8 other people's hands. So they shake everyone's hands except their own. That would be 1 less than the number of people in the room then, because you don't count yourself. So that would be times N minus 1. And then we said we had just double counted all of those handshakes. So that answer would need to be divided by 2. So we have N times N minus 1 over 2. And then you can go back to your table from earlier in the lesson and plug all of the numbers of justices in and see if the results match, and they do. Here I'll go ahead and show it for 9. If we have N equals 9, then we would have 9 times 9 minus 1 all over 2. That's 9 times 8 over 2, which does indeed give us 36. So that one does check. And if you look back, they all do. To wrap this all up, we're going to go through some examples and decide if the type of reasoning used is inductive or deductive. So in question 12, after failing the first 2 tests in math class, John decided that he better start doing the homework regularly. Well, that's inductive reasoning because he based his conclusions on 2 specific examples and assumed that if he continued to not do his homework, that pattern of failing would continue. In 13, Marlene was having a hard time keeping up with the minimum payments on her credit card, so she started to make a budget to make sure she wouldn't spend more money than she was making. And that last phrase there is the key here. This is deductive reasoning. She's not just basing this on a pattern. She's using a universal fact that if you spend more than you make, you will fall behind on your payments. In 14, in spite of his friends' pleas, Mark tried to drive home after drinking too much. None of them were surprised when he got busted for DUI. Well, this is deductive because it's not based on a pattern, it's based on the fact that the law says it is illegal to drive drunk. So they've used a rule or a fact to come to their conclusion. And then 15, my favorite professional team started off the new season with 12 wins and 0 losses. So I'm sure they're going to make the playoffs. If you know a little bit about sports, this one actually depends. If it were baseball, this would be inductive, because with baseball there are so many games that the first 12 games would really just be an initial pattern that you were assuming would continue. With football, on the other hand, if you win the first 12 games, there aren't enough left. You almost have to make the playoffs. So in that case, it would be deductive. In question 1, we're supposed to use inductive reasoning to find the 5th square number. So looking at the square number illustration here, it looks like to get from the first to the second, we add 3. And then to get to the next one, we add 5. And then to get to the next one, we add 7. And that gets us from 1 to 4 to 9 to 16. So looking at what we added 3 and then 5 and then 7. So inductive reasoning would lead me to believe that I would probably add 9 on the next one. And so to get the 5th one, I would suspect that that would be 16 plus 9, which is 25. In number 2, same idea for pentagonal numbers. So going from the first to the second, we add 4, and then to get to the next one we add 7, and then to get to the next one we add 10. So it's looking like each time you add 3 more than you added before that. So I would probably need to add 13 to get to the 5th one. And so the 5th one then would be 22 plus 13, which is 35. Now in 3, they're giving us some formulas, not really showing you where they came from, but giving you formulas that will allow you to find all of these different numbers. So the formula for triangular numbers, square numbers, pentagonal numbers, and then we want to use what those look like to try and figure out what the formula might be for hexagonal numbers. So looking at these before they were simplified, it looks like all of them start with an n over 2. So we've got that in the hexagonal formula. And then it looks like for the first part of what's in the parentheses, it starts with 1n and then 2n and then 3n. So I would suspect this time it would be 4n. And then looking at what is subtracted, it starts at -1 and then 0 and then 1. So I would suspect that this time it would be 2. So I would suspect that my formula was n over 2 times the quantity 4n minus 2. So then in 4, we're just going to use all of those formulas from question 3 to fill in this table. And for the ones that did simplify, you can go ahead and use the simplified version. So for triangular numbers, we have n times n plus 1 all over 2. And using a graphing calculator or a spreadsheet to fill in this table would save you a lot of time. And so plugging in 1 through 7 into that formula, the triangular numbers then are 1, 3, 6, 10, 15, 21, and 28. And then the formula for square numbers after it got simplified is n squared. And so those would be 1, 4, 9, 16, 25, 36, and 49. The pentagonal numbers, it doesn't simplify. We've got n over 2 times the quantity 3n minus 1. And so those numbers end up being 1, 5, 12, 22, 35, 51, and 70. And then for the hexagonal numbers, we just figured out that that would be n over 2 times the quantity 4n minus 2. And so those end up being 1, 6, 15, 28, 45, 66, and 91. In 5 and 6, we're asked to find a counterexample to the given conjecture. So in 5, every 8-legged creature is a spider. Well, a counterexample would be any 8-legged creature that is not a spider, so a scorpion, for example. In number 6, no number with last digit 0 can be divided evenly by 3. Well, a counterexample would be a number with the last digit 0 that can be divided evenly by 3. For example, 30. In 7 through 10, we're trying to decide if the reasoning is inductive or deductive. So in 7, Charles Manson has been denied parole 12 times. So our conclusion is that applying again would be a big waste of time. Well, that's inductive reasoning. We're basing our conclusion on 12 specific examples, and we're assuming that pattern will continue. In number 8, in this state to be a nurse you need at least a 2-year degree. So when I was in the emergency room, I asked the nurse where she went to college. Well, this is deductive reasoning because the conclusion that she must have gone to college is based on a rule that in this state, that's what you need to be a nurse. In 9, we got 4 inches of spring snow last night, so instead of the softball game I had scheduled, I'll make other plans. This is deductive reasoning. It's based on a rule that if you get that much snow, the softball game will have to be canceled. In 10, last night while playing blackjack, the dealer's first card was an ace 4 times in a row, so I really couldn't believe it when it happened again on the next hand. This is inductive reasoning. It's based on 4 specific examples, and while we're not assuming that the pattern will continue, we're using those 4 examples to assume that the pattern can't continue.